Alrighty, welcome everyone to day 6 of our continued efforts to complete all of the Advent of Code challenges. Today's problem is an interesting one, I guess. I guess I've said that for kind of all of them. But today we are working with orbits. So, for part 1, the question is to answer how many direct or indirect orbits there are in the map input they give us. So, for the input they give us, which is nice and long, each line lists an orbit. The 3 letters here on the left are what is being orbited, and then the 3 letters here on the right of the parenthesis are what is orbiting. So it is our job to build up a visual tree of orbits, similar to one I'm going to post here that they show on their webpage for the question. And the question is to answer how many indirect and direct orbits there are given this input. So a direct orbit is pretty obvious. So their example is that D directly orbits C. However, indirectly, D is also orbiting B and COM, which is the center of mass, which is the center of the entire thing. So the question stands, how many orbits is that? Well, D orbiting C is 1, but also because it indirectly orbits B and COM, that is a total of 3 orbits. And the question can get a lot more complex. For example, L directly orbits K, but then indirectly orbits J, E, D, C, B, and COM for a total of 7 orbits, whereas COM orbits nothing. So, given this input, we need to build up a tree, which I can already see is going to be hard because we're going to have a lot of dangling planets while we build up this tree. But then we have to calculate how many total direct and indirect orbits there are. So, this will be fun. So to get started, is there actually, hold on, is there a COM in here? There is a center of mass. Okay. That helps out a lot. I'm trying to figure out how do I want to build up this map. Obviously, we're going to have just a bunch of orbits. And that will be kind of hard to deal with. Let's try this. So, of course, we're always going to need to load in our input. And this is equal to our file util, and load the file from res day6-1.txt. So we're going to load this in, and my plan for right now is to load all of these in and save them as a relation of orbit. That say YJR orbits VQ9, just save them all directly there into some sort of list. And then from there, I would like to then build up our tree by selectively picking and going through that list and finding the relevant bits, I guess, from there. So, to start up and build up this map, let's actually do this. Let's do a map of string and then list string. So this is going to be orbits, and it's going to equal new hash map. Okay. And so let's go through all of the lines of input. So let's call this an orbit in input. And then for each orbit, we're going to go ahead and just split it. Call it orbit data, orbit split on the parenthesis, which is that one, right? Correct. Okay. So it's on that parenthesis. Go ahead and split it. Alright, go ahead and split it. And because it's regex, we have to do weird stuff. But either way. So there's our orbit, and position 1 in this will be our list here. So we're actually going to use a nice function here. So it computes if absent. So we're going to make a list. This is going to be orbiting whatever. The names I'm just kind of, yeah. And we want to get orbit data 0. And then if it is absent, we want, it's what, K, I think. We just want to return, actually, let's just return a new hash map. Okay, sorry, I was forgetting what this is. But anyway, so for those of you who've never seen this, this is Java 8. There is a method now in maps called compute if absent. And what it does is you give it the key. If that key exists in the map, it will simply return its value. However, if it doesn't exist, it will then call this lambda function, which in this case, we tell it to return an array list, but it also adds it to the map. So before, you would have to write something like this, where you would get the key from the map if it was null, or if the value of it was null, you either create a new array list, add it back to the map, and then do your logic. This just kind of compiles down to a one-line, easy to write thing. Great, it's a great method. I've actually used it a lot. I've really liked it. It's a nice method to have that just simplifies code that would be otherwise annoying to constantly write stuff. Anyways, so now that we have our orbiting list, we can just go ahead and add in orbiting data 1 here. And in theory, this should straight up just build up a map of all the keys, so every planet and what orbits it. From there, what we can do now is we can start at COM. So how do we want to compute this? So from COM, everything that orbits the center of mass is a direct and indirect orbit of just a 1. There's only one orbit around it. If we branch out, so in this case, to C and G from their example again, that 1 is now being done twice, so there's 2 there, plus it's 1 orbit. Okay, I just had to think about the problem here for a second, because trying to wrap my brain around what this is asking is a little hard for me right now. But I believe what we can do is we can just write a method here called get total orbits, provide it a list of orbiting, and also a int depth. And I believe we can recursively call this, and it'll correctly compute. So if we return integer, so in here, if we say int I equals 0, and then we do a for loop, we also need our hash map here. So actually, let's just do this. Let's call a string current. Let's call it current mass. It's not really a planet, but I'm just gonna call them current mass. So current mass, the orbits, and then our current depth. So if we do for string orbiting on orbits dot get current mass, this will go through all the things orbiting it. So we would actually call this total orbits. We would actually call this from here, pass it through COM to start, because that would be the starting center mass, and provide it orbits, and provide a depth of, in this case, 1 is what it starts at. No, depth is 0, I believe. It's either 0 or 1, I don't know right now. I believe it's 0. So everything orbiting this one, so I is 0, this is what we're returning. Return I. Just sum orbits, call sum orbits equals 0, return sum orbits. So for each one, sum orbits plus equals 1 plus all this sums, and the now center of mass is the orbiting, call orbits, and then we call depth plus 1. And it's actually not plus 1, it's depth. So this does start at 1. I think this is all we need to do. So what this method is going to do is it's going to sum up the number of orbits by doing this recursively. So back to our example, for B, it would go through here. COM would only return B, so that'd be the only string coming out of here. It would then add depth, which is 1, plus everything that orbits it. So for G then, then for this method for B, you'd get to here. The sum orbits would return first for G, the depth is 2, so we return 2 plus everything beyond it. H would then be the only one beyond it, depth of 3. Nothing is beyond it. Oh, this isn't going to work for H then. So how do we get H to return 3? I guess we always start it equal to depth. Or we just do if it's a list. Hold on. So going back to CM, so we're doing around COM. COM, there's only one orbiting it, and that is B. The depth of B, or depth is currently 1, so B would return 1 plus everything orbiting it. And then we go to G, which is a depth of 2. It'll return 2 plus everything orbiting it, which would then be H. H is nothing orbiting it. This wouldn't run, so we wouldn't get that depth effect. So we need to do size equals 0, sum orbits plus equals depth. I think that's all we need to do. In theory, we could split this and do if else, but this is fine. This will work just as fine. Let's give this a run, and I am curious. I don't think this will work, but it might be pretty close. Let's just see what we get. All right, go ahead and run. Building. Oh, I gotta run the correct day. I keep doing this. Run today's code. And we get a null pointer. Oh, it's a leaf. Ah. Let's do this. There's no pointer because it doesn't even exist in here. So actually we'll just do orbits dot contains key current mass. If it doesn't contain it, there, else do this. Okay. Now let's give it a shot. Is this our answer? No, too high. Okay, so it's too high. So going back to their example here. So I might need to write things out. Actually, I'll try and use my head, and I'll try and put the infographic on here with how this is going. So we call total orbits on com. So we call it on com. We set the depth to 1, and the only thing orbiting com is B. So it would be, actually, depth should start at 0. Because the depth is 0, we're calling B at the depth of 1. So we should start this at depth. I think that'll fix this issue. Give that a shot. I still need the check here, just so it doesn't air out. This is a much smaller number. It's still too high. Probably because we don't need this depth here anymore, because now we already have depth calculated there. And I will apologize for me being a little hard for me to talk and explain what I'm doing, because I'm trying to process in my head what my strategy is while also trying to explain and help teach you guys what my thoughts and plans are. And it's a little hard for me to think and do both, so I do apologize for sometimes being a little slow on saying stuff and whatnot. But I believe this will work. I have to wait here a second. I've been submitting answers too quickly. Hey, we got it right. Nice. Okay, so I was right. So I'm sure if I had the infographic I'm going to be showing you guys on screen, or I did show you guys on screen, I'm sure if I had that, I would have got this a little bit quicker. But yeah. Yeah. All right, let me read part 2, and I will get back to you guys. Okay, so part 2 is the same thing. We're still dealing with the orbits. Now we are asked to figure out how many orbit transfers are required to get from where we are to where Santa is. So I'm guessing somewhere in here there is U. Yep, so we are currently orbiting PFG, and Santa is currently orbiting 9FD. So the question is, how many orbits does it take us, or how many orbit transfers does it take us to get from where we are to where Santa is? And basically we use our map to know where we can transfer to in order to get to him. Let me think about how this is going to work. Part 1 was not too hard. The theory behind part 2 is maybe a little harder. Okay, so I think I have the theory and how you solve this question. In order to solve this question, you need to find the path from U to Santa. And in order to do that, you need to find the tree that gets you there. So given that, here again, I'll show you their infographic here. Given their infographic, their example, we are orbiting K, Santa's orbiting I. We need to find the tree that gets us from K to I. Now to do this, I believe what we can do is in our list here, I believe we can find where U is, and then from there we can find the node that us and Santa share that is the deepest in the path from the center of mass to us and to Santa. So again, using the infographic here, we are orbiting K, Santa's orbiting I. If we take the path from the center of mass to us, we go center of mass B, C, D, E, J, K, us. If we take the path from center of mass to Santa, we go center of mass B, C, D, I, Santa. If we were to compare those paths, we see that D is the deepest node that we both share. Therefore, we can calculate the path from us to Santa as, in reverse, our path J or K, J, E, D, and then down Santa's path of D to I. using that knowledge, I think that's the strategy I'm going to employ here. So I'm going to leave this. I'm actually going to do part 1, because this one does have two basically different inputs that aren't going to be similar. Okay. So we're going to make a public string or public list. We're going to make a list string. This will be returned the path. So this is get path to object. And we're going to need basically this to object, and this is the orbits. And what we're going to do is we're going to do this recursively again, because again, we are orbiting a planet, so we aren't actually a node in this orbit, because we are orbiting, nothing's orbiting us. So doing this recursively, ignore this for a second. I'm just doing that just so I have it there, and then return path. So orbits, and then there. So what we're gonna do is we have where we want to go. We just need to find what it is currently orbiting. So for string orbiting in orbits dot get. We need to. Oh, never mind. We need to go through each one. Orbits, and this is the key set. So we need to find what the object we want to get is currently orbiting. So, this is a string. Orbit, just call it orbit center. So we will do a check. So if orbits dot, if the orbits dot get orbit center dot contains to object, then what we are going to do is we have path up here, so it'll be equal to a new, actually no, just leave it like that. So the path will start at COM, and we will set path here equal to this, but we want the to object now to be orbit center. And in the end, this will return path. Actually, new array list, and then path dot add to object. Hold on. Try to figure this out here. If to object equals center of mass, so this is, we've hit the very top, we will set path equal to a new array list, path dot add center of mass, and then we return path, else we go through this for loop, and we set path equal to that, and then we do path dot add the orbit center. Let's just do that. Okay. This should give us the path from wherever we want to get to the center of mass. So let's just verify this, I guess. System.out.println arrays dot arrays to string path to object. We got to give it u for where we want to go, and give it orbits, and then do to array new string array. Okay, run this, and please, fingers crossed. I don't think that, yeah, it's common com. That didn't work. Oh, we don't need to do this. That should fix that. The double comma at the beginning. Okay. Did I even see you in here? I don't see you. My bad. No, we do need this. I'm just adding the wrong thing, and we want to add in to object instead of orbit center. There we go. And now is U the very last thing, and we are orbiting PFG. Correct. Okay, so I think this method works. It gives us, so our current orbit is really deep in here. So this is the path from the center of mass to us given our input. So now we get a list string u path. I should just call this u path. Okay, so there's our path. Let's get Santa's path. And now the next thing to do is to find out the deepest shared node. And that's actually pretty easy to do. We just go for int I Okay, so this is kind of not using the system I already had, but I saw a method that gave me an idea. There was a remove if method in these lists here that's new in Java 8, but it got me thinking, instead of doing this, what if we did this? And actually, let's skip one ahead. While the ones in front are still the same. Actually, no, let's just do zeros because we'll kill the main node. So while that's true, let's remove the root nodes of both of these. Again, this will remove the node they share, but that's fine because we can just add one back to the end because that one node shared is just one jump. So remove them all, and then also remove length or size -1. So remove the last node, which is the us node. So remove our node we're currently, or our current node, and remove the Santa node because those, it's only, the math is only the jumps to get from our plane or our node to where Santa's node on. It's not the path from us to Santa. So we don't want these in here. And then I believe the distance is just the two sizes added together +1. Correct me if I'm wrong here, but I think that's it. So it was 341. We got 341 again. Never mind. I I think it's just we're off by like a number or two. I think we're just barely off. Let me test this with the known input here real quick. Because the path for part 2 is 5. 1, 2. It's just off by 1. So maybe it isn't off by 1 and we don't need to calculate that jump. And maybe that is the issue. Let's go back, reset this to that. So the answer then for us would be 340, not 341. And that is correct. All right. In my head, I can't think in my head right now why it's not +1. I think just somewhere with the jumps or double counting somewhere. I'm not entirely sure. Yeah, I don't know. But either way, we were double counting some jump or we were adding too many jumps. Either way, this is it. Honestly, today's problem wasn't that bad. If you can get the logic quickly, and especially like me, if you can figure out that this is how a quick from point A to point B in a tree works, it's not too bad. If you're newer to programming, the part 1 is definitely a really good challenge for anyone new to programming. It's not too difficult. It's a really good just a good thinking problem, and in my case a good way to learn maps and whatnot. But overall, I thought it was a really good problem. So let's currently recap what my solution was. So of course we read in our inputs, and from there we construct a map of all the nodes and what orbits that node, which is what this part here does. And then from there we recursively get the orbits around each node. So our recursive function here takes the depth we're at, and from there it just recursively goes down our tree and calculates how deep each node is and then how many things are orbiting it. And then it comes back up and gives us the total amount of direct and indirect orbits. And then from there, we find our tree, we find the deepest shared node by both us and Santa, and then from them we create a path using that deepest node and the two trees to get the distance from us to Santa and how many jumps we need to make. So anyways, hope you guys enjoyed today, and I will see you guys all tomorrow for day 7.